The goal of this presentation is to design a sustainable public pavilion. We have selected Australia to be home to our public pavilion located in Melbourne, State of Victoria. The site of the pavilion is on St Kilda Beach and covers an area of around 6,100 square meters. It is in close proximity with commercial and residential buildings, multiple beachside food and beverage outlets, and the Luna Park, Melbourne. St Kilda Beach has always been a popular spot for locals and visitors. This is how the area looked like in the past, and this is how the beach looks nowadays with our selected site pinpointed on it. We shall let you enjoy the breathtaking views that have been taken through a drone. Owing to Australia's sheer size and being located in the southern hemisphere, it has a unique and diverse climate classification, where the seasons of the year are also opposite to the northern hemisphere. Our site, pinpointed on the map, falls within the temperate climate zone. The average temperature is higher from December through February, which are the summer months in Australia, and gradually dropping to their lowest in the winter months of June to August, with precipitation varying throughout the year. As we can see from data analysis and climate consultant, most months of the year fall within the comfort zone in terms of temperature, with the minimum recorded temperature of 3 degrees Celsius in the month of August and a maximum recorded 37 degrees Celsius in the month of January. Sky cover ranges from the average high of 95% in the months of June, July, and the average low in the months of December and February of 17 to 18%. The wind wheel chart showcases the highest wind velocity recorded from the northern direction throughout the year, reaching its maximum intensity of up to 16 meters per second in the months of July, August, and September. Australia practices two main assessment methods by neighbours and the Green Building Council in Australia. Our pavilion is designed in a simple yet practical shape with dynamic features. It will serve the public as a shelter from sunlight, rain, and become a comfort zone throughout the year. We shall now present individual scenarios for each season without having any negative environmental impact and by using naturally available energy sources.
Scenario 1. In August, which is a winter month in Australia, the sun appears lower. In both summer and winter seasons, the sun path is predominantly from north direction on the selected area, which is why we have intentionally placed the longer side of the pavilion facing north direction. During winter, parts of the roof facing north and the sunlight direction rise, allowing more sunlight to enter the pavilion. On rainy days, however, in winter and throughout the year, the sensors installed on the pavilion allow the wings to get back to original position and release the glass walls hidden under the roof to create enclosure and shelter from rain. Scenario 2. During Australian summer, the sun appears higher, as you can see from the sun path animation. In the summertime, the dynamic sides of our pavilion roof are said to go down to create shade and comfort zone during hot and sunny days. Scenario 3. Spring-autumn months. In spring-autumn months, the pavilion wings are said to go up to allow the sunlight to enter. The roof is partially covered with monocrystalline solar panels, which are more energy efficient and preferred in temperate climate zones. Wind turbines are placed on the roof facing north direction, which brings more intensive winds. Both solar panels and wind turbines present sufficient source of energy to support the dynamic movement of the pavilion and are connected to battery to store the collected power. Materials. The pavilion is made of sustainable materials. The base represents a concrete slab with matte surface tiles. The dynamic columns are made of recycled stainless steel, which is rust-proof and durable. Roof shade is made of stretchable, waterproof and tear-proof fabric. The dynamic glass panels are hidden under the roof for pavilion enclosure. IES data and analysis. To assess the performance of the pavilion, we have created models in IES for each scenario for solar and airflow analysis. If we compare daylight illuminance on the floor base of the pavilion, we can clearly see the illuminance is lower in the summer and higher in winter and autumn-spring seasons, which is what we aim to achieve. As the base case of our pavilion is similar to enclosed winter model, we have taken the winter scenario as the base case and provided the following data and results on the IES analysis. If we take winter scenario as a base case, we have achieved 59% daylight factor reduction in summer, and if we take summer scenario as a base case, we have achieved 59% daylight factor increase in winter. We have also provided the simulation of external and internal airflow, which is predominantly from north direction of the pavilion. The data is provided per season. We thank you for your time and acknowledge the support.